저번 시간에 한 거를 이렇게 다시 한글로 리뷰를 하면요. 네, 저번 시간에는 우리 뭐 계속 배우고 있죠. 네, 유니폼 배웠고, 그다음에 익스포넨셜 배웠고, 그다음에 노멀 랜덤 베리어블 가우시안 배웠고, 가우시안은 중요하다. 왜냐하면은 뭘 하던 간에 네, 가우시안 디스트리뷰션이 나올 가능성이 굉장히 높기 때문에 이제 어제도 네, 선거가 있었는데 대표적으로 선거 같은 게 네, 우리가 가우시안을 이용해서 뭐 이런 득표율 뭐 예를 들면 뭐 이 후보가 30%의 득표를 했다 그랬을 때 뭐 30%가 예상이냐 만약 예상은 30%를 할 것 같다 그러면은 30%를 가운데로 해서 35%도 될 수 있고 65%도 될 수 있는 건데 그럼 분포가 어떻게 될까? 그런 분포를 모델링 할 때 일반적으로 가우시안 분포 혹은 노멀 분포를 따른다라는 걸 했었고요. 그리고 이제 우리가 이제 derived random variable에 대해서 했었는데 그러니까 x가 이제 어떤 pdf fx와 pdf f of x를 갖고 있을 때 우리가 이제 다른 랜덤 베리어블 y가 그러니까 x로부터 어떤 함수 gx로부터 유도될 때 우리는 이 y를 derived random variable이라고 부른다고 했죠. 그래서 일반적인 G에 대해서도 그러니까 derived random variable 정의되긴 하지만 뭐 우리가 가장 많이 쓰는 리니어한 거에 대해서 생각을 해보면은 예를 들면 ax 플러스 b다. 뭐 이런 식으로 되었을 때 y가 그러면은 우리의 목표는 x를 알고 있죠. fx와 이제 cdf와 pdf로부터 이 x를 알고 있을 때 과연 y의 cdf와 pdf fy of y는 뭐냐? 혹은 pdf fy y는 과연 뭐냐? 요게 우리가 이제 알고 싶은 건데 그래서 쭉 우리가 그러니까 이런 어떤 그러니까 약간의 트릭을 따라 가지고 쭉 계산을 하게 되면은 만약에 a가 0보다 크다라고 하면은 네. pdf는 fy of y는 네, 1 over a f x of y 마이너스 b over a로 나온다 라는 거를 우리가 했었죠. 네. 그렇다라는 거죠. 네. 그래서 우리가 예제로 봤을 때 예를 들면은 유니폼이 x가 유니폼일 때 x를 리니어하게 트랜스폼 하면은 걔도 유니폼이 나온다. 그렇죠? 그리고 x가 노멀일 때 우리가 리니어하게 트랜스폼 하면은 ax 플러스 b도 노멀이다. 근데 이제 민과 베리언스는 달라지죠. 그리고 x가 익스포넨셜일 때는 ax 플러스 b를 하면 걔는 익스포넨셜이 아니다. 왜냐면 b만큼 시프트가 되니까. 근데 b가 만약에 0이다. ax라도 아니다. 왜냐면 a가 네거티브가 될 수 있으니까. a가 포지티브다? 그러면은 이제 익스포넨셜로 나오죠. 네, 그렇습니다. 그래서 조 밑에 저 이그젬플은 네, 집에서 한번 해보시면 될 것 같아요. 저번 시간까지 한 거에 대해서 질문 있으신가요? 네. 제가 깜빡 잊고 챕터 다음 렉처 노트를 아직 안 올렸어요. 그쵸? 네. 우리 수업 시간이 남겠는데 오늘 이것만 하면은 네, 어쨌든 그 다음 번을 해보도록 하겠습니다. 질문 있으신가요? So any concern for the previous lectures? Okay, so and let's move to the next topic. Okay, so this case, we gonna think about the very special the derived random variable. Okay, so first let's think about x, random variable x that has a uniform distribution between 0 and 1. Okay, this is a random variable x. Then let's consider a function fx. This is a general function, but importantly, this function satisfies all property of CDF. This function is a general function, but simply it satisfies by all property of a CDF. That means f of minus infinity is 0 because this one satisfies all property of the CDF, and f of positive infinity is 1. And it is monotonically non-decreasing. That means f of b is larger than equal to f of a if b is larger than equal to a. Okay? Then what else property? Okay, so and there might be more properties, but this is the critical one. Then importantly, this is the first one. Then it should have the inverse function. So that means invertible. So fx satisfies all property of the CDF, and fx is invertible. Let's assume that this fx satisfies these two properties. Okay. Then let's think about another random variable that derived from this x using the inverse of this fx. Okay, so this is the y, the derived random variable from x using this inverse function of f. Okay, so in this situation, let's think about what is the CDF or PDF. What's the distribution of y? Y is f of minus x minus inverse of f and x. So in order to obtain the CDF of y, fy of y, by definition, this is the probability that y is less than equal to y. Then this y can be substituted by probability that f minus of x less than y. Okay? Alright. So here, the important thing is this fx is non-negative, so it's always larger than or equal to 0 because it satisfies the property of the CDF, right? That means then x is from 0 to 1. So that means this function is function that this function is equal to from R to R function. R to R, so the real number to the real number function, that is from 0 to 1 to the positive 1, some 0 to some positive number. So the inverse is, this is the positive, so the inverse is the other way around, from positive to the positive. From positive to positive is the inverse, and the fx itself is positive to positive. So that means if we take the fx of this one and this one, let's think about f of f minus 1 of x and f of y. So let's think about let's apply that. So fx to the both sides. Okay. Then first of all, because the f satisfies the criteria of of the CDF, that means FB is larger than or equal to FA if F for any of the B is larger than A. That means because Y is larger than this value, so Fy should be larger than equal to this value. Is it right? So first, is it right? Because of the F satisfies all property of this one. So if this value, if the inverse of Fx is larger than less than or equal to Y, so F of this one should be less than or equal to this one. Okay, that's the first one. So and the second thing is this Fx, this the Fx itself, this function is monotonically non-decreasing. That means it's almost one-to-one functions. So this amount of this property should be equal to the probability of this one. Okay. Then if we go a little further, F and inverse, that is X. Probability that this is X is less than or equal to F of Y. Okay, so you got to here. So the probability of F, so the CDF of Y is equal to the probability that X is less than or equal to F of Y. F of Y. Okay. Right. Okay, so here is the typo. This should be not Fy, so this is just the Fy. Okay, so this is the typo. Okay, let's think about. That's a little weird. Okay. So let's think about this one in this case. So here we know X is uniformly distributed between 0 and 1. So here, so this is, how can I say that? F of X of Fy. Because X is because this is by definition being expressed by CDF of X. Okay. So what is this value? Because X is uniformly distributed. So if we draw this one, CDF of this one, it has PDF is uniformly distributed between 1 and 0. So the PDF is like this. 1. So this is the PDF of X. So the CDF is given. This is the CDF of X, right? Because X is uniformly distributed between 0 and 1. So X of X is X. So X here, follow that. This is the X. Okay? Then this one, this value, become f of y. So you got it? Okay, here is the conclusion. So let me summarize. Let's think about x is a uniform distribution between 0 and 1. And y is, then for a function f satisfying the property of the CDF, then if y is defined or derived by the inverse of f from x, then y's CDF is fy. That means y is a random variable with CDF of f. That's the point. So here is the given uniform distribution. Then if we apply the certain CDF function to that uniform function, uniform random variable, then we can get the new random variable with that CDF. So that means if we want to generate or design certain random variable with some specific CDF that we want, then we can actually generate anything from the uniform random variable. So let's think about. So here is the bottom line is like that. So in this situation, the wide CDF become, the conclusion is like that. So the f of y. So we actually show that x is uniform and y is derived from certain the inverse of the certain function. Then y has the CDF of that function. So that's the conclusion. So that means here is so let's think about you want to make a new random variable with the certain CDF, right? So that's our goal. But basically we don't know how to make how to gather numbers, actual numbers from those the random variables. So then in that case, but important thing is if we know if we have the random variable of the uniform distribution, then by applying inverse of the CDF, then we can get the values for y. So it's like that. So this is important in your homework. So the second homework. In the second homework, the last problem is little programming homework. That actually asks you generate. Let's think about the 1,000 numbers from exponential distribution. But how you can generate the 1,000 numbers from exponential distribution? You can use it like this. So you can easily generate 1,000 numbers from uniform distribution, basically. So the every the code provide the number generator from uniform distribution. Then from those the uniformly distributed numbers, how you can generate the exponentially distributed one? Then you just apply the inverse of the CDF of the exponential. Then you can get the numbers of the exponentially distributed numbers. So that's the point. 자, 여러분 다시 제가 설명을 드리면은 한국말로 다시 설명을 드리면은 x가 유니폼이다. 그리고 y가 어떠한 f의 인버스다. 그랬을 때 fy를 구하게 되면요. 그러니까 CDF를 구하게 되면 바로 요 f, 인버스 하기 전에 요 f로 바로 나온다는 거죠. 이 말이 뭐냐면은 우리가 어떠한 그 랜덤 디스트리뷰션, 그러니까 어떤 랜덤 디스트리뷰션을 구하고 싶은데 실제적으로 그 어떤 랜덤 베리어블로부터 뭐 숫자를 구한다거나 거기서부터 나온 그 샘플들의 숫자를 구한다거나 혹은 뭐 그게 분포가 어떻게 되는지 알고 싶을 때 그거를 실제로 어떻게 구할 거냐라는 문제에서 우리가 일단 유니폼을 알고 있으면은 유니폼에서부터 다른 어떠한 디스트리뷰션도 우리가 유도할 수 있다는 게 이거의 핵심이죠. 네. 그렇습니다. 오케이? 네.
저 함수를 익스포네이션으로 정하면
네네, 그렇죠. 네, 그렇죠. 그러니까 익스포넨셜의 fx는 뭐죠? 1 마이너스 2의 마이너스 람다 x 요거죠. 네, 그러니까 요거의 인버스를 구해서 그거를 x에 적용하면은 나오는 y는 익스포넨셜을 따르는 랜덤 베리어블이 된다는 거죠. Any question? 자, 질문 있으신가요? Okay, so we can actually see this one in other view. Let's think about x. X is a random variable with CDF of f of x. Then f of x is invertible. Let's assume that. Then here we derive new random variable. Y is f(x) of x. This is our new random variable. Then what's the sample space of y? In this case, 그래서 y의 sample space가 뭘까요? What's the sample space of y? Sample space of y means the range of values that y can have. That means yes. So y should be 0 to 1. So this is the sample space. Okay. Okay. Then let's calculate what's the CDF or the real CDF or PDF of y. So then is the same. So probability that y is less than y, and this is probability that y is f of x less than y. Okay, and then f(x) is invertible. So we can inverse it. Then without change of this the comparison mark. So x is less than or equal to fx minus 1 of y. Okay. So you got to here. Because we apply the f inverse to this side and this side, there's no, because it's a positive to positive, it's a positive to positive function. CDF, f is a positive to positive function and it's monotonically increasing. So there's no change of this, the comparison sign, and this relation is a hold. All right. So here, what is this value? Because y is defined in this way, that means x is inverse of y. So it is x is less than x. Okay? X is less than x. Because this value is small x. Okay? Then this is definition of the CDF of x. So it's a CDF of x. This is f(x) of x. and fx of x is y. Okay, so it's y. That means CDF of y is just y. That means y is uniform distribution between 0 and 1. So here, y is uniform distribution of 0 and 1. So basically, by applying, the certain CDF or the inverse of the certain CDF, we can actually generate, any random variable, or from any random variable, we can convert it to the, the uniform random variable. Okay. So this is some special case of the derived random variable. This one is very useful because in a practical application, when you generate random numbers, for example, if you want to generate random numbers from, let's say, okay, so the exponential distribution or somewhat complicated distribution. So it's very difficult to generate random numbers from those distribution. However, if you use such a technique, then you can easily do that. Then you're gonna practice these kind of things in your homework. In your homework, so for your homework you can use the MATLAB because I believe our school still has license for the MATLAB for student. But if you have some hard difficulty to use MATLAB, then you can use instead of R. So R is somewhat similar software with MATLAB, but it's free. So you can freely download the R, then you can just provide. So it's free to use either of the software. Definitely, if you want, you can use C program. 네, 그렇습니다. 질문 있으신가요? 자, 시간이 많이 남아서. 시간이 많이 남았구나. 자, 그러면은 우리 이제 summary. Okay, so let's look at this summary. So in this chapter, so we look at the continuous random variable. Then we discuss the cumulative CDF and the PTF, blah blah blah. And expectation is given in integration of the x times the PTF of x, and the expectation of the certain function of x is we just replace x with g of x. And here is common random variables that we look at the uniform, exponential, and normal random variables. Then we also discuss about the derived random variable g of x. All right. So any questions throughout the whole chapter 2, lecture note 3? Okay. So 유준아, 내가 혹시 프로그램스에 올려놓은 거는 안 가져? 다운로드 받았니? 지금 다운로드 받을 수 있을까? 블랙보드 있거든. Okay, so I actually get already get feedback from the previous after you got the midterm or final or homework. There's certain the comments that the midterm or some exam problems are very different style. Then you actually look at throughout the homework or during that handled during the class. So I don't know why, because I think everything is the same. But because of the comments, so I actually prepared some of the sample problems from previous midterms. So this one is uploaded in the Blackboard. So let's look into these problems for shortly. 자, 여러분 제가 다른 학생들한테 이야기를 들으면은 시험 문제가 너무 어렵다. 시험 문제가 수업 시간에 다른 거랑 전혀 딴판이다. 라는 코멘트가 자주 오는데요. 제 생각에는 별로 그렇지 않은데 그런 코멘트가 와서 실제로 시험 문제에 어떤 게 나오는지를 작년에 나왔던 시험 문제를 기준으로 해서 보겠습니다. 당연한 이야기지만 PDF가 이거일 때 expectation을 구하시오. 이런 문제 이런 문제 안 나옵니다. 그 당연한 이야기예요. 그건 계산 문제잖아요. 그렇죠? Okay, so definitely I don't give you a problem such like the but this is your PDF and what's the expectation of this random variable. There's no such a problem because that's only for the calculation problem. So instead, I try to make a problem that you need to apply the basic concepts of these probabilities. Okay, so let's look at first one. Okay, let's think about you want to make a circle with a rope, but the length of the rope is followed the exponential distribution with mean is 1. That means, let's think about L is length of rope. Then L follows exponential distribution with a certain lambda. And another condition is the expectation is 1. That means L is 1. Okay? So in general, expectation of the exponential random variable is lambda. So in general, expectation of is given as lambda. That means lambda equal to 1 in our problem. So L is exponential random variable with parameter of 1. Okay? Then we want to make a circle with this rope. Yes? Okay. It's 1 over lambda actually. I'm sorry. Because lambda. 유준아, 다시 그 옛날 책으로 써볼래? 그 렉처 노트 우리 방금 보여준 거 쓰리. 서머리 부분을. Okay, so L is exponential random variable with lambda. Then, in that case, the expectation is 1 over lambda. So, that is 1. That means 1 over lambda is 1. That means lambda is 1. So, this is 1. Okay, so here we want to make a circle with this rope. Then the length of, so the round length of the circle is L. That means radius is L over 2 pi. Am I right? L over 2 pi is R. Then our goal is, let's use this in a round R. Then our problem says the expected area of the circle. That means we want to know expectation of pi r square. That is our what we want to know. Then next is everything is simple. So this is expectation of pi times 4 pi square over L square. So this is 1 over 4 pi expectation of L square. Because you know the PDF of the exponential distribution, you can directly calculate the square of expectation of the square of L, such as expectation of L square is given as from 0 to infinity L square and times CDF가 뭐 있죠? 네, 이렇게 기억이 안 날 때는 이거 참고하시면 돼요. 바로 이거 그래서 치팅 시트가 필요하다. 네, 왜냐하면 기억을 못할 수가 있으니까. 람다 to the e to the minus lambda L dL. So this is the calculation, but in this case lambda is 1, right? So this is 1 and 1. So you need to calculate integration of L square times e to the minus L. Can you integrate this equation? If you have enough time, you may be able to do, but by myself, I cannot do that. I cannot do that. So instead, I do not use this kind of approach. I do not use this kind of approach. Instead, I use variance of x is equal to expectation of x squared minus expectation of x of the whole square. So instead, I use these relations. It is you already know. So in here, expectation of x squared is variance of x plus expectation of x squared. So here is, so this expectation of L squared is similarly variance of L plus expectation of L squared. What's the variance of L? Because we don't know, we refer this cheating sheet again. If you refer this cheating sheet again, so 1 over lambda square. So it's 1 plus this one is also 1. So expectation of L square is 2. So the answer is 1 over 2 pi. You got it? So definitely you can spend the 20 minutes to calculate this integration, but you can simply using the one you know in a minute. So either way it's fine. 자, 그렇죠? 네. 그다음에 next problem. Okay, next problem is when x is a geometric random variable, show that so x is a geometric random variable, let's say then show that probability of x is larger than b, even x is larger than a, is equal to probability that x is larger than b minus a. Here we say b is larger than a. And a, b are non-negative integer, so they are all integers. Okay? So this is simple because this is by definition it's the probability that x is larger than b and x is larger than a divided by probability that x is larger than a. Because b is larger than a, this one is probability of x is larger than b divided by probability of x is larger than a. Okay? Then this is 1 minus probability that x is less than equal to b by 1 minus probability that x is less than equal to a. Because x is a geometric distribution, so the f of x do you have a lecture 2 note? Lecture 2? Because you need to use lecture 2 here at this point. P 곱하기 마이너스 보고 할게요. 네. Then do we have to calculate it? I don't know. So I don't know whether it's in the. Is it in? Okay, so unfortunately, it's in my note, so you have to calculate. Anyway, so but the calculation is not difficult. So anyway, if you calculate it, this one is 1 minus p to the x. Okay, so if you calculate it, so it's like that. So 1 minus this one. So this is the CDF. 이거요? Geometric에서요? Okay, so let's calculate this one first. PDF F in PMF, because it's in PMF is P times 1 minus P to the X minus 1. So if we summate, so the fx of x is summation from, let's use u. U is from 1 to certain value of x, p and 1 minus p to the x, in this case u minus 1. So if you calculate this summation, you can see it is equal to that. Okay? because see there. Then this one is 1 minus p to the 1 minus p to the x, 1 minus p to the b over 1 minus p to the a. So this is 1 minus p to the b minus a. This is again 1 minus x of b minus a, and this is equal to this one. This one is exactly equal to this one. So we have shown. So in the problem, a is larger than b, but it doesn't matter because I assume that b is larger than a, so it doesn't matter actually. Do you remember what we call such a property? Memory leaks. Because you may remember that if x is, let's say x is exponential. Let's say x is exponential. This one is also. And we say that's a memory leak. That means x never remember your waiting, your previous history. 네, 여러분, 과거는 중요하지 않아요. 네, 여러분의 여자친구, 남자친구의 과거는 중요하지 않다. 과거는 다 잊어버립니다. 뭐가 되는데? 그러니까 우리가 지금 x가 b보다 크고 x가 a보다 이미 컸어요. 커져 있어요. 그 다음에 b보다 더 클 확률이 얼마인가를 집행하는 거잖아요. 근데 그거는 b와 a의 차이만큼 큰 거랑 같다. 그러니까 조금 그만큼 더 가는 거랑 그냥 아무것도 없이 가는 거랑 그 전에 기다렸다 가는 거랑 똑같다. 그러니까 그 전에 과거는 잊어주는 여러분도 지오메트리나 익스포넨셜 같은 사람이 되길 바라요. 네, next. Next question is a little bit tricky. Okay, there's a stick of length of 1 meter. So there's a stick length of 1, that is at this point we say 0, at this point let's say it's 1 meter. Okay, so then Okay, then our situation is like this. Okay, in here we actually mark the point at P. Small p. Okay? Alright? Then you actually split this stick at some point of u. That means we make two different sticks, and this point of view follows uniform distribution between 0 and 1. Then the question is, what's the expectation of the length that contain P? This marked point P. This is the problem. So you understand the problem? Okay? So let's think about L. L is the let's consider the L is the length. Length of the the part with this marked point. Okay? And this L is actually given as derived function of u, basically. Because the length is depend on the u. If u is this point, then we have to calculate get the length of this part. If u is this part, then we have to calculate this length. Right? So the length is function or derived random variable of u from u. So then this one is simple. If u is larger than p, u is larger than p in this situation, then length is u. If u is less than p, this one, then length is 1 minus u. Okay? So, we want to calculate expectation of L. This is, because L is g of u, then it is given in this way. So this is g of u and f u of u du because u is from 0 to 1. So it can calculate it in this way, right? Because L is function of g of u. And this function of g is given in this way. Okay, so first, what's the fu of u? One, because u is uniformly distributed. So fu is 1. So this is 1. And this function is given in this way. So let's do it in here. Then this is equal to, because if you look at this function, u is separated by p. So first we integrate from 0 to p. From 0 to p, u is less than p. So we have to use this function 1 minus u. 1 minus u du plus p to 1. For the p to 1, it's u. So u du. Then this one is equal to 0.5 plus P over 1 minus P. Then this is the expectation of the length that contains P. Any question? 자, 그렇죠? 네. 그래서 이거 이렇게 한다. 네. FUU는 다시 X가 CDF of FX를 갖고 있어요. PDF. 그쵸? 그쵸? 그럴 때 expectation of G of X는 그러니까 X에다가 G를 통해서 만든 랜덤 베리어블의 expectation을 구할 때는 우리가 이미 알고 있죠. G of X에다가 Fx dx를 해준다는 거 이렇게 해서 구하죠. 결국 이게 PDF, X의 PDF가 되는 거죠. 이거는 U의 PDF죠. 근데 U의 PDF인데 U가 지금 유니폼 디스트리뷰션이죠. 0에서 1 사이에. 왜냐면 막대가 0에서 1m짜리 막대가 있는데 거기 중간에 아무데나 자르는데 자르는 포인트를 유니폼하게 결정하니까요. 그래서 1이다. 그냥. 네. 네, 그 다음 next point, next problem. 질문 있나요? 네. Then next problem is in a jar there is in total n balls, and among them k balls are red and rest. That means n minus k balls are blue, black, whatever, blue, red and blue. And here then here we say x is random variable of, so then denotes the number of red balls when we drawing n balls. That's the random variable x. Okay. Then here the question is, what is the PMF of x? Calculate the PMF of x. So it's very straightforward. So PMF of x is the probability that x is equal to a certain number of small x. So then we just calculate what's the probability we get the x red balls from n total balls. So this is the simple high school level of the probability problem. So in order to choose calculate this one, so total number of cases is n choose large n choose small n, because that's the total number of cases we choose small n balls from large n balls. Ooh. Okay. Then, if we want to get the x red balls, small x red balls, we have to choose small x red balls from in total k red balls. So this is k choose n. Then rest of them. So rest of them should be blue. That means we have to choose small. So among n in total n minus k balls, we have to choose small n minus small k balls. So this is PDF of x. PDF of x. Okay. So it's a simple, the element, not the element. high school level questions. Then next is, please show that x approximately follow a binomial distribution when large n and large k are much larger than small n. So that's the the actual the true problem, actual problem of this question. So here we know. Okay, so the if we think the k choose n is by definition, by its definition, it is written as k factorial divided by n factorial. Oh, this should be there should be x. Okay, this also should be x. K should be x, and okay, I'm sorry. N minus x. I should be like this. Okay, so but k to the n, k to the x is x factorial of the k minus x factorial. Okay. Okay, you got it. Then here, and then let's think about. So in here, in our notation, that n is the much larger than n, and k is much larger than n. That means it also much larger than x, because n should be less than x. X should be less than n. Okay. So in this situation, if we focus on this part, so this part is calculated by k times k minus 1 times and blah 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 divided by k minus x times k minus x minus 1 times blah blah blah. But this one is cancelled by somewhere here, and this one is cancelled by somewhere here, and everything is cancelled by. So finally, this one is k times k minus 1 times blah 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 k minus x plus 1. So but here, if k is much larger than x, this value of k is very similar to k minus x, because k is much larger than x. So this is approximately, we can think k to the x, because there is the k to x terms. Okay, so this one can be rewritten as approximately k to the x divided by x factorial. Okay, by using this property, if we rewrite this one, it's almost k to the x divided by x factorial times n minus k to the n minus x to the n minus x factorial divided by n to the n over n factorial. Okay, so if we rewrite this one is equal to, if we re-summarize it, n factorial over x factorial times n minus x factorial, then here k over x, k over x, and n minus large k over n minus x divided by n over n. Okay, so this one. So okay, this one. First one is equal to n choose x. N choose x. Then this one is, we can rewrite it n times x times n minus x. So then we find this one and this term. So this one is then times k over n to the x, and this one is 1 minus n over k to the n minus x. So this is the PMF of x. So this form is exactly same with binomial. So binomial with parameter n, and in this case, what's the p? K over n. So this one is followed binomial distribution of n and k, large k over large n. Okay? Okay? Okay. Next. Next problem is a little bit more somewhat difficult one, but definitely you can do that if you think enough time. Well, if you think enough, if you think the more carefully, you can actually solve it, even though it looks really difficult. Okay, so let's think about x is a very random variable. P. Then y is derived random variable of x by log x. No, it's not right. Okay, so here y is ax plus b. Y is ax plus b, and a and b are both positive. Here, what you want to know is here we want to compare the expect. So okay, in general, for any random variable x, expectation of g of x is not equal to g of expectation of x. In general, so we actually already looked at it. So, but in here so for example, we actually derived a new random variable g that is log of y. Then here we want to calculate expectation of log y. This is the first one. So this is our first value. Then we want to compare this value with log of expectation of y. These two things. First of all, so the question is, by comparing this value and this value, which one would be larger? Or are they going to be the same? That's the question. Okay, this is the answer. All right. So how we can calculate how we can the approach this problem. So the simple approach is the draw a figure. So because the Bernoulli is x is a Bernoulli. Because the x is Bernoulli, so we can simply calculate the expectation of y. Expectation of y is p times a plus b plus 1 minus p times a. This is the expectation of y. Okay? So let's think about we want to draw a graph. X-axis is y. Okay? So here y, a and b, a and a plus b. So y can have value either a or a plus b. A or a plus b. Okay? Then this point. So if you carefully consider what this point means, this expectation is somewhere in the middle. That is proportioned by p. You see what I mean? So this one is actually way p for the a plus b, and 네. y는 b군요. 네. 여기가 b군요. 네. b라고 해요. 저 b랑 a 플러스 b 그 사이죠. 그래서 이게 여기가 지금 b고 여기 b가 되는 거예요. 여기도 b가 되는 거죠 다. 네. a가 지금 b가 되는 거예요. Okay, so it should be b here, right? So this point. Okay, so if you think about what this point means, if you know a little bit, so if let's think about if p is 1, if p is 1, then that value is become a plus b. If p is 0, that value is also b. That means that is in the middle point here. That is taking b part as a unit. From p, it takes it's a p or 1 minus. So let's look at, so this one is okay, so let me rewrite it. P and a plus p so this point is equal to b plus let's rewrite it to the pa plus pb plus b minus pb. Okay, so this pb is this is b plus pa PA. So this is the B plus PA, right? That means starting from the B, so because this difference is A, starting from B, we just take a portion by P. So this is a portion by P, and this portion is 1 minus P. So actually, this point is the expectation of expectation of the y. This point is expectation of y. So in other words, this expectation of y is the middle point between p and a plus p by taking the portion of p and 1 minus p. So like this. So this is b and p, then we take the portion of p and 1 minus p. This is the portion, okay? Okay, here it is. Okay, so let's let's think about here. We want to calculate, we want to see what is the log of expectation of y. Log of expectation of y. Then we draw log curve here. Log curve here. Then we project this part to this part. So this is log of e of y. This is the log y part. Log y part. 자, 여기서 빨간색 점이 this red point indicate log of ey, expectation of y, right? Because this point is the expectation, then we project to this log function. Okay? Then because we want to compare this one with log of okay, so we calculate this one. Then we want to calculate this one. Right? This one is given as because this is the expectation of gx, so this one is actually log when y equals p times p, is right? So if 1 minus p, so it's like that. So this one is p times log a plus p plus 1 minus p log e. Right? Because expectation of gx is g of x times p of x. So this is the probability that p, the probability that y is a plus b, then our function is log. So this part plus this is for the probability when y is b. So log of y. So okay, at this point, so if we also plot those ones, because this point is b, this point is log b. And here, this point is, let's see, log a plus b. Okay. Then, actually, we add log a plus b and log d with proportion of p and 1 minus p. That means this part and this part should be weighted by p versus 1 minus p. So that means this one and this one should be. So when you draw the line that goes, that directly connect this point and this point, then it should be divided by this point and this point should be divided by p versus 1 minus p. So that point is exactly to this point. Because in the x term, it is divided by p versus 1 by p. So for the same position, actually for the same the y value, one value is located on this the log function. The other is located on the linear function. However, what was the log curve looks like. Log curve is somewhat incorrect. It's 위로블록이라고 그러죠. Or in English, it's a concave. It's a concave function. So this one. So in here, red point is always larger than blue point. So we know that log of EX, EY is larger than expected value of the log Y. 이 개념은 간단한데 설명하려니까 시간이 많이 걸리네요. 시간이 벌써 죄송합니다. 22분이구나. 자, 말하지 그럴게요. 네, 그렇습니다. 네, 수고 많으셨어요.